and I will minimize this. And I guess a couple of things I would like to mention or to bring to your attention. Uh, First and foremost, I guess you know what's happening next month. We have elections, so I hope that you're already registered to vote. However, if you're not, I think you have maybe 1 or 2 more weeks. It seems like October 15th, 16th, 19th, something like that is the last day to register. So please, folks, get into the habit of voting. You may already be in that habit. If you are, fantastic. If not, please vote. I get sick and tired of people of hearing people brag about, oh, and we had 45% turnout, and that means that someone who got 23% of the eligible voters vote got elected, because if you have 45% turnout, 23% will win an election, and that's pathetic. That's not a democracy. Please, folks, get registered and vote. This is a crucial election in my mind. I think, boy, so many things are going down the tubes right now. We've got to take responsibility and vote. Please, please vote. Uh, any If you have problems with me saying this, I won't say it anymore. Otherwise, I'm probably going to say it until election day. So when I think of it, I won't think of it every day. All right. Any other issues, concerns, problems, whatever?
Where do we turn in the test?
Okay. Yeah. When or where?
Where?
Where? Okay. You have several options. Okay. You can attach it to an email and turn it into me that way. You can attach it to a Blackboard message and turn it into me that way. And I believe on Blackboard, I can't remember which week it is, whichever week I passed out the test and sent it, under that one you'll see there is a tab that says test 1 or something like that. And if you want to figure out how in the world to submit the test through that link, you can do that as well. I check those every week. I try to check messages every week, and I try to check emails every week. So I'm behind on emails right now, but I was catching up over the weekend, but then things sort of blew apart. So I had a faculty meeting or a departmental meeting on Friday, and then had other things come up over the weekend. So I didn't quite make it through all the uh, things on Blackboard, on email. One of the reasons is this is week 8, which means this is approaching midterm, which means my first mini-term class is coming to an end, and they were turning in things left and right, some old stuff, some for more current stuff, but I have, I would say, and this is a fairly conservative guess, that I printed off at least, I don't know if you can see it, that much material just from that class over the weekend, and I still have to grade it. Some things I went on and graded, so that's why I said that's fairly conservative. So I'm behind in emails just because they were swamping me this weekend, but that's good. I'm glad to get them, and this week I'm going to be grading like crazy because their term ends this week, and I get second mini term class starting, maybe 2 classes starting next week. All right, did that answer your question okay?
Yes, sir.
Probably far more than you wanted to hear, but okay, good deal. Any other issues, questions, concerns? Oh, yeah, I'm recording. I want to make sure I was recording that answer too. Okay, if nothing else, we're in Chapter 7, which is Applications of Integration. We're in Section 7.3, Volume, this time using the shell method. Okay, we talked about the disk method and then followed that up with the washer method in the last section, and now we're doing the shell method. We started this on Wednesday of last week, and here we pick up where we left off there. Now, just a little bit of maybe review, if I could get my PowerPoint to do anything. Okay, what we're doing here, we're revolving a shape, some type of a shape, around some type of an axis, okay? And in revolving that around an axis, we have the length of that shape. Now remember, here's what the washer method did. We would do the dx's here and do this length minus this length. Those would be the two radii, and it would be pi r squared for the upper radius minus pi r squared for the lower radius, and that gave us, and then the dx's, that gave us our volume. Because you see, the rectangles then were vertical in this case, and the thickness was, the dx, the length was the difference between those two radii, but it's the top radii squared minus the bottom radius squared, because you were dealing with the volume of the upper disk minus the volume of the lower disk, and that gave you the volume of the washer. With the shell method, the rectangle is done d-wise along the y-axis here, when it's the strips are parallel to the axis of rotation here. So that gives you a shell, okay? And what you get is, if you can picture this, the thickness of that shell is revolved all the way around the axis. So basically you only deal with one radius then, and that is the radius from the axis to that rectangle, okay? So 2 pi r is the distance that rectangle would go around the circumference, okay, times your delta y. And oh, I'm sorry, I left off the length. The length of the rectangle, you need that as a function of y as well, because you got a dy. So it's the length of the rectangle times the circumference that that rectangle travels, 2 pi r, and the r is p in this case, h is the length, and delta y is your thickness, okay? And that will approximate the volume, and you go from C to D because you're only doing from here to here. You don't have to worry about the hole in the middle. You're not doing that. You're doing the length of this rectangle times the distance it travels around the axis times the thickness of the rectangle, and that's it. And here comes Ashton. So let me admit him, get him into class, if I can find my pen. Oh, okay. Ashton's here. Okay, we're only missing Brandon. Has anyone seen or heard from Brandon? He's usually here. Let me make sure he's not out there waiting somewhere. Nope, just the three of you. Okay, hopefully he'll be here. All right. I guess here's a little other bit of news. I should have made this announcement earlier, and I disagree with this strongly, but I heard from the academic dean in an email that the college is considering running some classes on campus in large venues like auditoriums or wide spaces, actually on campus beginning in the spring. They are just now beginning to talk about this. Spring schedule's already been submitted. The planning process is so screwed up, but it seems like to me a terrible idea. Okay, now I think, and I'm going to voice this, I've already voiced it before, I think a far better approach would be let students who need to be on campus to attend classes, let them come, but set up a computer lab for them when they're spaced apart and let them do their Zoom or Blackboard Collaborate or whatever the instructor is using from the computer room, from a computer lab. And that way they can maybe not have to deal with trying to watch everything on a phone screen, which is really small and hard to do, I would guess. I use my laptop, but I know a lot of you don't. You may not even have laptops that have, you know, good wireless, situation, and you may be trying to do everything via a phone or a mobile device. And if that's the case, that's a tough thing to do. So I would think rather than having classes on campus, let students who need to come to campus and go in a safe environment where they can view their classes, but have everything still as a virtual. Now that's my opinion. Do y'all have any feeling on it one way or another? Which way would you rather do? Would you rather be back on campus? I mean, frankly, I would rather be back on campus, but I can't. The situation is not good for that. But what would be your feelings on it?
I feel like it's a good idea, but like for teachers like you have like a sickness. I think it would be better just be on like
Yeah,
computer wise, so it won't affect you physically and like
right.
I agree. You need to stay safe, Dr. Fowler.
Yeah, well, I appreciate that, but I think any instructor, whether they're young, healthy, everything that I'm not, uh, if they go down, I mean, if they get it, they're going to be out probably for 2 to 4 weeks or longer. And who's going to cover the classes then? You know, it's not just old sick people like me who are overweight and everything else. It's every instructor. Okay. Um, and I think students, if they can, probably shouldn't go to campus either. But if they need to go to campus, I think we ought to have that available to them, do just like they're doing now, checking temperatures, doing all the things, the safety precautions they are now, but having a place for them to be able to participate remotely if they don't want to do it the way they're doing now. But like I said, I'd rather see the whites of your eyes. I'd rather interact with you in person. I really dislike the virtual environment, though I think we got it down fairly nicely now. But the thing is, it's still not as good as seeing you. But it's not the time. I think Washington has demonstrated that over the weekend, didn't they? That it's not the time to be running around acting like the thing's over with. It's not. Okay, it's nowhere close. We're right now about 10%, I think, and that means if you get around a group of 10 people, the odds are one of those people probably is asymptomatic or pre-symptomatic, and you could catch it from them. So, hey, it's still not a good idea. When we get up past 65, 75, something like that percent, then it gets a little safer. But not right now. When that many people have already had it and have immunity, then the spread of the disease will be far less likely. But right now, it's not good. Okay, I don't know. That's my opinion, but I appreciate your comments. But if you could take a class on campus, would you rather have it on campus or would you rather do it remotely? Um, what's your preference?
I like campus better
I
for
do
me.
too. Yeah. Okay. So if you had the opportunity in the spring, you would go for it, right?
Maybe.
Maybe. Okay. Yeah.
I would.
Okay. Um, would you? Okay. Would you feel better if it was a computer lab and you were separated and all like that, and watching it on a laptop that was provided by the school or that type of thing, or would that be better than what you're doing at home now? Or how would that rate, would would that still be a lot less effective than having the instructor there? I think it would be, but I don't want to influence you in the classroom too.
I think it'd be better because we won't have any distractions away from us.
Right,
And like we have random students like right next to us on both ends, and then you know we're not gonna be as distracted since we
right.
don't know each other, and we're just gonna be paying attention to class. So I think it'd be better.
Okay, and which would be better, having the instructor there?
It'd be better with the instructor there
Right,
to some extent, but if like like me, I'm always prepared. I have everything ready.
right.
If somebody sneezes, I have my disinfectant spray.
Okay.
It's because I'm a germaphobe, so I really don't like anything germs or anything.
Right, okay. All righty. Okay, well, I'm going to be in a meeting in 2 weeks, I think it is, something around there. And I'm going to try to voice what I'm hearing from faculty. I heard that at the meeting on Friday, and also what I hear from students. So I appreciate your comments. All right. Anything else before we get back to the to calculus here? Okay. So this is what we were doing, and this is where we ended last week. So here's where, now I have to hit the screen before I can go. Okay. So you can approximate the volume of a rectangle by n such shells of thickness. Okay. You have n of them now. And they have thickness delta y, just like we showed here, length h of y, okay, and average radius, that p of y, okay. So the volume of the solid would then be approximately the summation from I equal 1 to n, you have n of those shells, 2 pi, I would take that 2 pi out, they did over here, 2 pi r radius, that's the p of y, that gives you circumference, the area around the axis that rectangle has traveled, times the length of the rectangle that went around there, times the thickness of the rectangle, delta y. And there you have your total volume of that n, of that shell, and then you add all those up from 1 to n, and that's what you get. And they pulled the 2 pi on the outside, 2 pi times the summation from I equal 1 to n of p of y, p of yi, that means the ith, for the ith shell that you're dealing with, what is the radius for that y, and then what's the length for that y times your thickness, which is always delta y. Now that approximation appears to become better and better and better as your norm for that interval, okay, the way you broke it down approaches 0. That means your n is approaching infinity. So the volume of the solid would then be that limit as your norm goes to 0 of 2 pi times this very thing we had up here, the summation I equal 1 to n of the radius as a function of y sub I, that's this way, the height, the length of that strip that goes that way times your delta y. That limit of that sum then becomes the 2 pi stays on the outside, the summation from C to D. Since we're doing delta y's, we go from C to D of P of y, H of y, dy. Think of this as 2 pi times the radius around that rectangle is going around, times the length of the rectangle, times the thickness of the rectangle. 2 pi r circumference times length times thickness. There's your 3 dimensions, and that gives you your volume. Okay, does that make sense? Okay, so here's the shell method. To find the volume of solid of revolution with the shell method, use one of the formulas below. Okay, now if it's a horizontal axis of rotation, then you use a dy. This is exactly backwards from what it was from the disk and washer method. Then if it was a horizontal axis of rotation, you use a dx, okay? With the shell method, your horizontal axis of rotation, you use a dy because that's what's going around. So you'll need your radius that you are from your representative rectangle to the axis of rotation. You'll need that as a function of y. You'll need the length of that rectangle as a function of y. And then, of course, you have your dy. So if it is a horizontal axis of rotation, the volume would then be 2 pi times the integral from c to d, that's where your limits on your y, p of y, h of y, dy, like we just showed. If it's a vertical axis of rotation, you're going around this way. Now your radius is a function of x. Your length needs to be a function of x because your thickness is a delta x, or later to be a dx. So the radius is the distance from this rectangle to the axis of rotation. Your height is a function of, h is a function of x here, from the line here to the line down here, and then your dx is here. Delta x is there. That's what you do, 2 pi, and this time you're going x going from a to b. Your variable is x. Here the variable is y. Here the variable is going from a to b, 2 pi times the integral from a to b, p of x, h of x, dx. So the issue here is find out what works best. Can you get your h function as a function of y and your radius function as a function of y? If you can, easy to do a dy. Here, if can you get the height function as a function of x, the radius function as a function of x, then the delta x is a piece of cake. Okay, so that's the shell method. So here's example 1. This will be on the next page, page 466. Okay, let me try to get some of this paper out of the way. Okay, and actually that previous box was on the top. Find the volume of a solid formed by revolving the region bounded by y is equal to x minus x cubed, and the x-axis, okay, that's where y is equal to 0. X-axis is y is equal to 0, and you're going from x equals 0 to 1. So there's your a to b, because you're dealing with x's here, about their y-axis. Okay, yeah, and they want you to use the shell method. You certainly could use the nah, this would not be as easy. I was going to say the disc or washer method. That would not be an easy thing to do, because then if you're going around the y-axis for the disc or washer method, you need your dy's, so then you would need this expressed in y. Hey, try to do that. Try to get x as a function of y from that function. Gonna be almost impossible to do. But in the shell method, it's already a function of x. You're going to use a delta x going around. That's going to be the thickness of the shell. Your limits are in x. Everything's in x. So the shell method is set up great for this one. Okay, so let's see if how they approach this. Okay, I was hoping they didn't have as much verbiage, but it's the same thing I just said. Here is the graph, y is equal to x cubed, x minus x cubed, and they show it's going from 0 to 1, revolving this around the y-axis. So draw your representative rectangle with a delta x here. Okay, now you'll need the rotation, the radius, to be a function of x, but look at that. the radius is just x. How far out here you are as x goes from 0 to 1. That's going to be really easy. The height of this is the curve to, this was y is equal to 0. Remember, when they say the x-axis, I always think y is equal to 0, okay, because that's what it is. So you're from y is equal to this to y is equal to 0. So that's your height here, x minus x cubed minus 0. And then you're going to go around it. So this is set up perfect. Whoa, I don't want them to show all the work. So let me get my pen, let me get my pad, and let's see if we can do it here. So where is my, there it is. Okay. All right. So the volume here, that's what we're looking for. Find the volume of the solid. And this will be, since you're using the shell method, is 2 pi times the integral of, and the integral is going from 0 to x, 0 to 1, since you're doing a dx here. I always like to identify what I'm going, okay. Your radius is this p of x, which is just x, times your x minus x cubed. That's your height, okay. Now let's think about it. 2 pi times the radius, that will give the distance that rectangle goes around the y-axis. The height of that rectangle is just your x minus x cubed, and the thickness of that rectangle is your delta x. There you have it, okay? Now, how would I solve this? We'll keep the 2 pi on the outside, that's for sure. And the integral will still be 0 to 1, which are very nice things to do. I would go on and multiply this through. There's no reason trying to do anything else. Just multiply through and make this x squared minus x to the 4th dx. And I think we can probably all do that integration, can't we? This is 2 pi times, what's the antiderivative of x squared? Anybody?
X cubed over 3.
X cubed over 3 minus, what's the antiderivative of x to the 4th?
X fifth over 5.
Perfect. Okay. We'll evaluate this from 0 to 1. So that's going to be 2 pi times 1/3 minus 1/5. And the good news is, with a 0 down here, minus 0, minus 0, minus or plus 0. I don't care, you know. That's it. That's the answer, but not worked out completely. Let's get this, if I can find it again. There it is. Let's get everything here over 15. And this will be 5/15 minus 3/15. So that would be 2/15. So this would be 4/15 pi, or 4 pi over 15, or something like that. Let's see how they did it. The distance from the center of the rectangle to the x-axis is just your how far you are from the y-axis. That's x, okay? The height of the rectangle is x minus x cubed, because you're going down to y is equal to 0. So subtract that from that, you still get that. The x ranges from 0 to 1, so this will be your volume, 2 pi times the integral from a to b. This will be 0 to 1. Your radius function as a function of x, which is just x, times your height function, which is x minus x cubed dx. Plugging in those things, it'll be 2 pi integral from 0 to 1 x times x minus x cubed dx. And let's see if they did it the same way we did. Yes, well, they reverse the order, which I think is very helpful here. 2 pi times the integral from 0 to 1, and they put the minus x fourth in front and the plus x squared at the back. Why, I do not know, but they did. Perfectly legal and legitimate. I would not have done it that way, but we didn't do it that way. When you did the antiderivatives, you got exactly what you did, only in reverse order, so everything's fine there. When you plug that in, 2 pi times a minus 1/5 plus 1/3, and they don't show you how. They just came up with 14 pi over 4 pi over 15, which is what we got, except I called it 4/15 pi. Same answer. Again, though, if you were doing WebAssign and they wanted the answer written as 4 pi over 15, they would tell you that 4/15 pi was a wrong answer when it's absolutely not a wrong answer. It would be perfectly correct. But see, the computer, basically, I'm sorry to say this if any of you love computers, they're stupid. They only do what they're programmed to do, okay? They can't interpret, okay? Now, artificial intelligence is getting really good at interpreting. We're not... WebAssign is not artificial intelligence yet. It's more artificial than it's intelligent. Okay, so don't be expecting it to be able to recognize those kind of things. So don't always believe it when they tell you it's wrong. See if you can get it in a different form, and if it likes it better. Okay. Any questions on example 1? Okay. Now, they're skipping example 2, so I'm going to go back and do a new share with the whiteboard. And now I've got to move things around here. So let me set this down so I don't drop that expensive pen. And now for some reason it's writing on the screen when I don't want it to write on the screen. When sometimes it won't write on the screen when I do want it to. So I don't know. It's obstinate that way. Let me see if I can clear that mark off the screen and scoot the screen as far to the left as I can so I get maximum white space for me, as far up as I can so I get maximum white space for me. Okay, and Jordan, I think I've got you moved as far to the right as I can. Let's see if I can move you any further. No, you're as far as I want to do. I don't know why your name alone is setting up there, but it is. All right, so let's do example 2. I think I'm going to get the book in my lap because I can't read that far away. Okay. Find the volume of a solid formed by revolving the region bounded by the graph of x is equal to e to the minus y squared and the y-axis bounded by the y-axis, and they say it that way. Whenever I see that, I want to, and I usually do, write x equal 0, because that's true of the y-axis. X is equal to 0 everywhere on the y-axis. Okay? And they're also telling us it's between the values 0, again, one of my favorite set of limits here, 0 is less than y less than 1. Okay? And you're revolving that about the x-axis. Now that I'll just let set as x-axis. We don't need that to call it y is equal to 0. This is just saying the axis of revolution is the x-axis. You just need an axis. There it is. All right, now that means I probably have to try to draw this thing. Boo hiss. Okay? But the good news is I'm only going from 0 to 1. So let's see what we've got there. Okay, I'm going to draw my y-axis here, my x-axis supposedly there. Okay? Now, when x is equal to 0, no, I'm sorry, let's do when y is equal to 0, x is equal to 1. Y is equal to 0, x equal 1. Okay? When y is equal to 1, this will be e to the minus 1. Now, I'm going to have to pull out my handy dandy calculator here, which, by the way, is my telephone. Okay, if I can find the calculator. There it is. Okay, I'm going to have to turn it sideways to get the scientific notation here, because I'm needing to do, and on this calculator, I have to enter the argument first and then the function. So I'll put enter a minus 1, I enter the 1 first, change signs to a negative, and then do the E key. Okay. And that didn't work. Okay. Oh, e to the x key. I'm sorry. I did the wrong thing. Let me clear that out of the way. A 1, negate it, and then do the e to the x key. There. And we get, I don't know where the thing is, I can't see it, but you get an answer of 0.36 blah, 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 blah. Okay? So your y value there when x is equal to, when y is equal to 1, and I really have messed up my graph here. Let me go back and change a few things. Okay. Let me expand this a little bit. Okay. So let's put x equal 1. Let's put y equal 1 up here, y equals 0 there, x equal 1 here. So x equal, when y is equal to 0, x is equal to 1. When y is equal to 1, you're around 0.36. So that would be somewhere right around there. Okay? Now, what's it doing in between that? Well, it's an exponential curve. I'm going to cheat and look at the book, okay, and see that it comes down and kind of bulges here a little bit. But it's a nice smooth curve. My line isn't very smooth, but that's what you are. And you're going, this is y is equal to 1 here, this is x equal 1 here, this is the x-axis, this is the y-axis. Okay, so basically you're doing this part here and revolving it about the x-axis. So it's going around like this. So everything is in terms of y. X is a function of y, x is a function of y, your limits are y, so we're doing a dy. There's your dy or delta y. I like to call it dy. Okay. Okay. Whoops, that's supposed to be my nice straight rectangle. Haha. Okay. And what is my radius here? The radius is y. The p of y is equal to y. Okay? My length here is this value here. Your h of y is equal to e to the minus y squared. Okay? And I think that's all we need. So what's the volume? The volume is 2 pi r, 2 pi, that's that, the 2 pi r, 2 pi, that radius here, that gives you the distance that rectangle travels around the x-axis. Okay, so the 2 pi is on the outside. Since you're dealing with y, that's going from 0 to 1, and you got a dy here. I like to always make sure I've got the limits matching my variable, and it is. And the radius function is y, okay, and the length function is e to the minus y squared. There you have it. Your 2 pi y is the distance that goes around the x-axis. E to the minus y is the length of that segment that goes around the y-axis, and dy is the thickness of that segment that goes around the y-axis, x-axis. So there you have your volume. Okay. Now, how do we evaluate this? What would be your suggestion? I'm giving you a hint. I can't do that one in my head. Okay, nowhere close. So I'm going to do a u substitution. Let u equal the innermost part of the more complicated part of this. Well, y is pretty simple. E to the minus y squared is not that simple. What's the innermost part of that e to the minus y squared is minus y squared. Let that be the u. The next statement then would be then du is equal to, anyone tell me that? Minus 2y dy. Well, we have a y dy here. We don't have a minus 2y, so let's divide everything by minus 2. Okay, and that way this will go out, and that gives us a y dy, which is exactly what we've got. So this will be the volume will equal to, and we need a minus, and this 2 will cancel that 2 out. It's minus pi times the integral. Okay, we need to change our limits now. When y is equal to 0, that's here, u is equal to 0. Okay, when y is equal to 1, u is equal to minus 1. Okay, and that would then be e to the u, because that's what we let the u be, du. Okay, we got a problem, Houston. You got the upper limit being less than the lower limit. So let's flip them, and when you do that, you lose the minus sign. Okay, so that's going to be a pi times the integral from minus 1 to 0 of e to the u du. I think we can do that one, right? What's the antiderivative of e to the u? Is e to the u. And we got that pi out front. Let's not forget that. Okay, and this e to the u is evaluated from minus 1 to 0. Okay, so that's going to be pi times e to the 0 is 1 minus e to the minus 1. There's your answer. Now, if you want a approximate numerical answer, we can do that too. Just pull out your calculator. Okay, turn it sideways to get scientific notation. And I think I'm going to do the parentheses first. 1 minus, and then to do my exponent first, I do a 1 again, change its sign, and then do e to the x, and have an equal sign. Okay? And multiply that by pi, which I do have a pi key on here, and that gives an answer very close to 2. I got approximately, if I could find my, there it is, approximately 1.98, goodness, it goes on forever. I'm just going to call it approximately 2. Okay, it's 1.9858653, which is awfully close to 2. Okay, they did 1.986. Yeah, that would have rounded to 1.986. That's still awfully close to 2. Okay, so sure enough, that's what they got for an answer. Now, there is a little exploration box here that I don't know if you feel like doing or not. It said to see the advantage of using the shell method in example 2. Okay. I really don't want to write all this down. I don't know if you got your books in sight so you can see it. Hold on just a moment here. Goodness gracious. I'm trying to charge my watch and it doesn't seem to be charging well. Okay. So what I'm going to do is hold it up for you. And the one we just did here, the one we've got here, worked out very nicely when you did the shell with dy. If you're trying to get to a dx and do the disk method, which would be the delta x's, I will draw that in for you if I can find what I did with my pen. There it is. The disk method would have been, yeah, well, it would help if I got my pad down. Okay. The disk method would have been a wedge here, and this would have been a disk, not a washer, and you're going around the x-axis, so you would need this as a function of x. So this h as a function of x, we would need to solve this for y. Okay, so this would be x is equal to e to the minus y squared, and let's take the log of both sides. Okay, and I shouldn't have put it down there. So this would have been log x is equal to minus y squared, and then divide by a minus 1, and that would have been a y squared is equal to that, and then take a square root. Y is equal to the square root of a negative log x. Okay, now where is this going from and to? Okay, well, we know the dx is going from this point right here, and if you recall, what is that point there? Oh boy. We had it somewhere here. I guess I just did it on my calculator. Okay, what that value was, and that was basically 1 over e. Okay, because when y is equal to 1, this would be e to the minus 1. X would be that. So x is going from 1 over e to 1 here. Okay, I like that upper limit. This one's sort of a pain in the neck. And then you would need the square, and you would do that using the disk method. And remember, the disk method was pi r, okay, and your r here is this r right here, the radius going across here. That's your h of x, which we found to be this, the square root of minus log x, okay, squared, pi r squared dx. Well, when you square this, you get minus log x, so then you would have the integral from 1 over e to 1, that's your x limits here, of, and you got the pi on the outside, pi r squared, which would be a minus, so let's pull the minus out here, the log x dx. Now, there is a way to do that. We haven't hit it yet, but there is a way to do that. Okay. I'm trying to think if a u substitution will work. It won't. There is a technique to do it, and that would be a real pain in the neck to do. Once you learn the technique, it's not that bad, but without that, it's almost impossible to do. So you see, there is one example where the shell method is going to work out so much easier and nicer than the disk method. Okay? Now, that leads us to what the next slide is. I think this is in the book, so let me go back to the book here. Okay, and I think we're in 7.3 still. So let's go back here and go resume slideshow. Let's see if that works. Yeah. So let's go to that comparison of the disk and shelled methods. Okay. The disk and shell methods can be distinguished as follows. For the disk method, the representative rectangle is always perpendicular. Let me get my pad here. Let me see. I've got too many moving parts here and too small a desk. Okay. Is always perpendicular to the axis of rotation. The representative rectangle is. So here we're doing if you're going around the y-axis here, for the disk method, your rectangle is always perpendicular to that. The y-axis is vertical, so your rectangle is horizontal. Okay, and then you do your dy's here, and then your pi r squared. The r is this length from here to, well, this is a washer method. Pi r squared to the bigger radius minus pi r squared from the smaller radius, which if you just pull the pi's out there is big R squared minus little r squared times dy, because your increment here is dy. Okay, so that's your disk method. With a horizontal axis of rotation, then again the rectangle is perpendicular to that, and it's this rectangle here, so it's the same deal. Pi times this one squared minus that one squared times your dx. That's your thickness here. That's the washer method. They call it disk, but this is washer in this case because we're going around an axis on both of these, that you have a hole here and a hole there. Excuse me. Now, for your shell method, if the axis of rotation is the y-axis, something parallel to the y-axis, then the rectangle is parallel to the y-axis, because this now is going around the axis like this. That rectangle is going around, so it's 2 pi times that radius, okay, whatever the distance from your axis to that point, the middle of that rectangle, 2 pi r, that's going to be, they call it p, 2 pi p, 2 pi on the outside, times the height times your dx. Okay, so that's that one. If you're going around the y-axis here, then it's around the x-axis is horizontal, your rectangle is horizontal. That means you got a dy here. Okay, they call it delta y. And then your 2 pi times the radius, that gives you the distance that goes around that axis, times the height. You need that as a function of y also, because your delta y is there. Okay, so that's the comparison. Which works best? Whatever's easiest. Okay, be lazy. Find the way that makes it easiest. So here we move, I think, to example 3. And by the way, this example, you can go to larsoncalculus.com for an interactive version of this type of an example. Okay? And here's what we got. Find the volume of the solid form. Excuse me, just a minute. My throat's clogging up. Okay, find the volume of the solid form by revolving the region bounded by the graphs of y is equal to x squared plus 1. So there y is a function of x. Y is equal to 0. That's y is a function of x. X equals 0 and x equal 1. Those are the limits of your integration. So there's your limit about the y-axis. Okay? So the y-axis is here. Okay? I should have probably drawn it a little further over, but we'll leave it like this. X squared plus 1, y is equal to x squared plus 1. That would be a parabola that's elevated by 1. Okay? So when x equal 0, this is 1. When x is equal to 1, this is 2. Okay? So we're doing this portion here. Okay? This portion of the curve right here. Okay? And doing around the y-axis. Okay? This is the y-axis here. Okay? So you're doing dx's here, so this would be your rectangle here would be represented that way because you're doing dx's from x equals 0 to 1. Okay, and this is y is equal 1 to 2. You don't need that, but I just drew it in there for you. Okay, so this certainly looks like this will be a shell method. Okay, would be the easiest way to do there because you got your dx's. Okay, 0 to 1, everything's in terms of x's. So this will be 2 pi. Okay, the volume is equal to 2 pi times the integral from 0 to 1 of your radius. Well, what is your radius here that you're revolving around? It's just your x value. So x times, what's the length of this rectangle? It's x squared. It's 1. I mean, it's 2. You do need this. 2 minus x squared plus 1. So I'll write it out. 2 minus an x squared plus 1. You see, that's the height of that rectangle that you're revolving around the y-axis. Okay, your thickness is your dx, and your radius was simply your x. Okay, as x goes from 0 to 1. So let's clean that up a little bit. 2 pi integral from 0 to 1. Okay, 2 minus x squared minus 1. So 2 minus 1 would be 1. So let's make this x, that's x times 1, minus x cubed. Boy, that looks familiar, doesn't it? Okay, dx. Okay, I think that does it for us. This will be 2 pi, if I've done it right now, x squared over 2 minus x fourth over 4, evaluated from 0 to 1, and this would be 2 pi times 1/2 minus 1/4 minus 0. So this will be 2 pi times 1/2 minus 1/4 is 1/4. So this looks like it's going to be pi halves. Let's see how the book did. No, they didn't. I did something wrong in my problem. Oh. I did this volume up here. I wasn't paying attention. I did this volume here. What it is, the volume between that and the y is equal to x axis, it's down here. Okay? It still works best. Okay? Now okay. But guess what? Guess what? Even though I did it wrong, okay? Look at what we've got here. We've got a cylinder of radius 2, right? I'm sorry, radius 1. And height 2 is what I would say. I'm going to subtract this from it. So a cylinder of radius 2, radius 1, height 2, would be 2 pi r squared. This is the height. R is 1. That's your radius, 1 squared. That'd be 2 pi minus pi halves would be 3 halves pi. And we wound up getting the same answer. I did it wrong because I did this one up here. I didn't pay attention to this. I said it and then I didn't pay attention to it. We're doing this area down here. Okay, so let's do that correctly this time. Okay, but anyway, that's the answer we got that way. I'm going to erase this. Okay, now let's do it the right way. Okay, we got the right answer this way, but that was a little extra work. 2 pi times, now what's the height here? The height here, the radius is x, the p of x is still x, the height here is now x squared plus 1, and then the thickness is dx. Okay, so just like we did before, but now it's even easier to do. This integral will be 0 to 1 of x cubed plus x dx, and that would be 2 pi times x to the 4th over 4 plus x squared over 2, evaluation 0 to 1, and that would be 1/4 plus 1/2, so it's 2 pi times 1/4 plus 1/2 is 3/4, and 2 will go into 4 twice, and you get 3 halves pi, or 3 pi over 2, whichever way you want to do it. They always like, or most of the time they like to do it 3 pi over 2. So it's the same answer either way. Okay, this was much shorter. If I'd have been paying attention, we'd have gotten there very quickly. All right, that's how we did it. Let me erase, let me see if I need to. Yes, I do. So let me come down here and erase my scratch. All this time I haven't been erasing. The washer method requires 2 integrals. This part down here would have been this one would have been a disc, so it's not a washer. This would have been a disc, that would have been a washer. You have to add those two together. You could do that. It'd be okay, but it's 2 integrations. Now, actually, the bottom one is not necessary to integrate it because that's just a cylinder of radius 1, height 1, and its volume would be pi r squared h, which would be pi times 1, which would be pi. And then you do the upper part here, but here you have to get this in terms of a function of y now, because you're doing a dy, and that would have been y minus 1 is equal to x squared, and take the square root, and you have x is equal to the square root of y minus 1. Now, why didn't you do plus or minus? Because you're over here in the positive first quadrant. So that's what you're doing from there. So that's how they get the radius here to be y minus 1, square root of y minus 1. But that's a pretty easy thing to integrate, because that's your inner radius. Your outer radius is just 1, okay? But when you square this inner radius, that's just going to be y minus 1. So you can go, and the y now is going from 1 to 2 up here. It's doable. It's a little more work, in fact, quite a bit more work, but it's still easy integrals to do. It's just you have to do more work to get to them. Much easier to do. Oh, and this, they're showing it. This one, they're integrating that one, and that gives you pi. Okay, they're integrating this one, 1 minus this one. That's pi times 1 squared minus y minus 1. That's a minus y minus a minus, so it's plus. So that gives you 2 there. Okay, again, more complicated. Pi times this is just pi. This is a lot harder to evaluate, but it's still not bad. That would be 4 minus 2, which would be 2 minus 2 minus a half would be pi halves. So it would be pi plus pi halves, which would be 3 halves pi. Okay, which is what we got the other way. But if you do the shell method, it only requires a one integral if you do it right. And this time we did, doing from here to here. The height here is your x squared plus 1. Your distance here is just your x, and you're going from x equals 0 to 1, because your delta x is your integration. Okay, there it is, one integration, 2 pi times the integral from 0 to 1 of x times x minus x, or x squared plus 1. That would be x x cubed plus x, and that integrates to be x fourth over 4 plus x squared over 2 from 0 to 1, and that would be pi halves times 3/4, which is 3 halves pi. Okay, just like we did it the second time. Okay, oops, how can that be? That is the last slide in the slide set, but we still have 2 more examples to do. So that's why I was wanting my watch to be working. It finally is charging now. I don't know why it wasn't charging before, but my phone still works. Yeah, we've got about 30 minutes. Let's see if we can get example 4 done, and possibly example 5. So let's go back to the whiteboard. And I don't think any of you need that any longer, do you? If you do, speak now or forever hold your peace. Okay, so let's do example 4, top of page 469. Oh boy. A pontoon is to be made in the shape shown in figure 734. Thank you so much for not putting this on the slideshow, so I have to try to draw this sorry thing. The easy things they put on there, the hard ones they don't. I'm going to show you what it looks like. The trouble is I can't see if I've got it on the field of view or not. Okay, can you see that pontoon? Do I need to go up, down, right, left, forward, back? You see that blue pontoon? I'm not hearing any answer. Well, I'm not hearing an answer, so I don't know if you saw it or not. I'll do my best to draw it. Okay, but there was the figure. Pontoon is designed by rotating the graph of, so here's your graph, y is equal to 1 minus x squared over 16, I believe it is, from -4 less than or equal to x less than or equal to +4. Okay, about the x-axis. Okay, I sure don't want to draw this, but I guess I'm going to have to. Okay, here will be my y-axis, sort of, and this is sort of my x-axis. Okay, let's go 1, 2, 3, and 4, -1, 2, 3, and 4. Okay. Now let's see if we can plot this. That is an x squared. When x equals 0, y is equal to 1. So there's 1. Okay. When x is equal to 1, then this will be 1/16. 1 minus 1/16 will be 15/16. Not going to drop too much, but a little bit, somewhere right in there. When x is equal to 2, this will be 1 minus 1/4, because that would be 4 over 16. 1 minus 1/4, that would be 3/4. So it's dropped a little bit more. Okay? And then when x is equal to 3, that would be 1 minus 9/16, and that would be 9/16 for 16/16. Is that 5/16? Something like that. And when x is equal to 4, that would be 0. Okay? Now, if you go on the negative side, you get the same results, because this is symmetric about, it's an even function. This is an even function here. This is an even interval here, so it's an even function. Now that's pretty ugly, okay? And then it goes down to -1 here, so the bottom half is going to look something like this. Is ugly, something like that. So that's supposed to be a pontoon. They have a little more pointed at the ends than I do, but anyway, that's what you got. Now, and you're revolving this around the x-axis, which I've already done, because this is the x-axis, okay, and I've drawn that revolved around there, and x and y are measured in feet. Fine, okay. Find the volume of the pontoon. Okay, now here you have y as a function of x. We're revolving around the x-axis. Everything's in terms of x, okay? So it just looks like to me that delta x's would probably be the way to go, okay? I'm going to call it dx's, okay? So basically what you've got is a slice here, okay? That's going to be a disk, okay, because the rectangle is perpendicular to the axis of rotation, okay? And what is this? This is y is equal to 1 minus x squared over 16. And you're going to there, so that's your height, that's your radius, that's your disk, okay? So basically the volume there. Now I'm going to try to make it a little easier, because this volume is exactly the same on this side as it is on this side. So why not double it? So we'll get 2 times the integral. Oh, and we got a pi because the volume of this is pi r squared. Okay, that's the really ugly part here. Your radius here is that thing, and we've got to square it. So we'll get to that in a moment. Pi r squared, so we're going to have to do the y squared here. So let's do that now. That would be 1, square the first term, minus twice the product. That would be 1/8 x squared plus the second one squared, which would be x fourth, over 16 squared. Is that 256? I think it is, but don't trust my memory. Okay. 16 squared is 256. That's right. Okay. All right. So that's okay. The 2 is there because you're only doing half of it here. Okay. So we're going from 0 to 1 in your x's. 2 times pi r squared. This is your r squared. 1 minus 1/8 x squared plus 256 x to the fourth. Okay, dx. Pi r squared dx. Okay. That's a little bit nastier to integrate, but it's still not bad. Okay, so this will be integral of 1 is x. Integral of this will be minus x cubed over 24. This is the part that gets nasty. Plus x to the fifth over 5 times 256. I'm just going to write it as 5 times 256. Isn't that what I said it was? Yeah, 256. Okay. And that's going to be evaluated from 0 to 1. All right. So you got a 2 pi out front times. Now the 0 is not going to give you anything. So you get a 1 minus 1 over 24 plus 1 over 5 times 256. Okay, 5 times 6 is 30, 28, 12. Okay, the hard part of this problem is the fractions. Okay, so this will be 2 pi times 1280 minus, this will all be over 1280. Okay, I'm going to pull out my calculator. Okay, 1280 divided by 24. Oh man, I thought that was going to come out even. Yuck. How did that happen? Oh yeah, because we divided by 3. That's right. Yuck. So it's not 1280. It's not my least common denominator. Let's do 1280 times 3. 3840. Let's do that one. This is getting really ugly. I hope I'm doing it right. Otherwise, I'm going to be really disappointed I've wasted all this time. Okay. Least common denominator, I think, is 3840. Let me just check in the book and see if things are looking this bad there too. Yes, I think they are. Um, they skip so many steps it's hard to tell. Okay, and this will be, let's see if we do get the same answer. Okay, if I could find my pen, there it is. Okay, 3840 minus and divided by 24 160 plus 3, I believe it is. Yeah. All right, so let's do that math. 3840 minus 160 plus 3 equal it's got to be an easier way to do this. Okay. Well, one thing will make it somewhat easier, if I wish I had seen this earlier, but no, it's a little bit late in the game. Let's divide 2 into that, and that gives us 1920. Okay. Um, I'm going to skip all, I mean, they skipped all the steps. I'm going to skip them too. I'm sorry. We're just running. Well, we're not out of time yet. I thought we were. I'm sorry. I thought we were. We are getting low on time. What they come up with is 64 pi times 15. Okay, that's what they get, which they say is approximately 13.4 cubic feet. Now, I'm just going to see if my numbers come out anywhere close to that. Okay, 3683, I think that was, divided by 1920 equal, and multiply that by pi. Whoa, I just multiplied twice. Yuck, I messed up my calculation. I have to go back. I think I may have done a dumb mistake somewhere here, so rather than try to slug through that again, we'll just leave it like that. 13.4 cubic feet. The hard part is the fractions, okay? It's not the calculus. The calculus was really pretty easy. We got pi times x minus x cubed over 24 plus x to the fifth over 1280. And then from there it just got nasty, but they skipped so many steps there. I'm convinced it still works out well. Okay. So anyway, it said to use the shell method in that example, you would have had to solve x in terms of y up here, and that would have been a real big pain in the neck. That would have been y plus or minus 1 is equal to a minus x squared over 16 and I would have turned that around to be x squared over 16 is equal to 1 minus y, and then this would be multiply both sides by 16, and you get x is equal to 4 times the square root of 1 minus y. I think that's it. And that would have been what you had to go from. That would have really been a nasty integration, but doable. It would have been doable. A U substitution be required. This way, the fractions were nasty, but I guarantee you the fractions are going to be nasty there because the answer is going to be the same. You're still going to have to deal with all the mess. Okay, so that way, disk method, far easier than the shell method. Now, let's go on. How are we doing? We got 9 minutes. Let's see what we can do with example 5. So let's clear the screen here. Any questions before I clear this? I know I did a lot of talking there and it came out messy. Let's clear this and let's at least set up number 5. Find the volume of a solid form by revolving the region bounded by the graphs of y is equal to x cubed plus x plus 1. Y equal 1 and x equal 1. About the line x equal 2. Okay. Now they have a figure in the book. Again, they didn't show us this one. This is a pain in the neck. So let's draw this best we can. Y-axis here. Okay. X-axis down here somewhere. And when x is equal to 0, okay, we're going to have to draw this in. When x equals 0, your y is equal to 1. So let's do a 1 here and a 1 there. So x equals 0, y is equal 1. Let's do when x equal 1, y is equal to, and by the way, y is equal to 1 is this line right here too. Okay. And when x is equal to 1, y is equal to 3. So there's 2, 3. So this will be up here. Okay. Now this is some sort of curve that goes up. I'm using the book to something like that. Okay. So there is this part. Okay. This part, y is equal to 1, is that part. X equal 1 is this part. So it's this region here. You're going around x equal 2. That's over here. So this is your axis here. Okay. Should be a straight line. And this is revolving around here. Now, if you wanted to use a washer method, you would have to do a dy. You don't have this as a function of y. You cannot get this as a function of y. So you're going to have to use a dx here. So let's do a little rectangle here. Okay, there it is. Your height here is this thing minus 1. So your p of x is, no, your h of x, sorry about that. The h of x is equal to x cubed plus x, because it's this thing minus 1. Okay, your p of x, okay, now p, remember, is your rotation as you go around here. Well, this is 2, x equal 2, and this is x equal x. Okay, so your p of x is 2 minus x. Okay, your h of x is this, and then of course your thickness is dx. Okay, so what your integral then is, your volume is equal to 2 pi, because it's the shell method, that radius, which is integral, and the integral's going from, if you're doing x's here, it's 0 to 1, because you're doing dx. Okay, your p is 2 minus x, and your h is x cubed plus 1 plus x dx. Okay, that's your thickness. Let me make sure I'm doing right. Yeah, I believe that is correct. Let me make sure that's what they got in the book. Now, we're 4 minutes. Let's see what we can do in 4 minutes. I think the only way to go with this is to multiply, and that's just a simple foiling. If I could get my, here we go. So let's foil this. There's a v is equal to 2 pi times the integral from 0 to 1. Good limits here. Okay, now let's foil this. 2x cubed your outer is plus 2x, your inner is minus x to the fourth, and your last is minus x squared dx. Now, no, the book doesn't like doing it that way. They like to get it in descending order of power. Guess what? It really doesn't matter. We can integrate it just like that, and since we don't have much time, let's go on and do it. Integrate this, and this will be 2x to the fourth over 4, so that would be x to the fourth over 2, plus 2x, well, that's just x squared, minus x to the fifth over 5, and minus x cubed over 3. Evaluate that from 0 to 1. Thank goodness for those limits. Okay, so the volume here is 2 pi times, that would be a 1/2 plus 1 minus 1/5 minus 1/3. Okay, still messy. Okay, least common denominator I think is 30, so that's going to be 2 pi times, least common denominator is 30, that'll be 15 plus 30 minus 6 minus 10. I think I'm doing this fast. Let's go on and cancel out the 2 and the 30 and make it 15. Okay, and let's see what we've got there. I have 1 minute. Let me see if I can punch my calculator that fast. Okay, I think this is fairly simple. Oh, I'm going to need a pi, so let's turn it sideways. Okay, 15 plus 30 is 45. I wish I'd have just done that in my head. Minus 16. That would be a 29/15 pi. So I think that's the simple answer is 29/15 pi. Let's see if the book got that. Yes, that's exactly what they got, and they didn't mess with rounding it off either. Okay, thank you so much. 29/15 pi. So we'll just leave it like that. Okay. And that finishes section 7.3, and we're out of time, I realize. Homework exercises here. Always do the concept checks. Think through those. Homework exercise, any of the odds 3 through 11. They're all at Calc Chat. 7's at Calc View. 13 through 21, they're all at Calc Chat. 17's at Calc View. 23 or 25, they're both at Calc Chat. 23's at Calc View. 27 is at Calc Chat and Calc View. 29 or 31, both at Calc Chat. 33 or 35, both at Calc Chat. 37's at Calc Chat. 39's at Calc Chat. Any of 41's at Calc Chat. Any of the either 43 or 45, both at Calc Chat. And any of the odds 47 through 61. They should all be at Calc Chat. All right, and we'll begin next time with 7.4, arc length and surfaces of revolution. Any questions? I know that got sort of fast at the end, but are there any questions? Okay. Now just looking ahead, we're going to finish 7.4. Going to do 7.5. I've got to go back and check my course description and see if we need to do 7.6 or 7.7. I've always done them in the past, but they did change what they wanted us to do in this course, and they may have left those off, so I'll find out. So we're getting fairly close to the next test, which means be getting your last test in. All right. Any questions? Okay, I'm going to clear that slide if it'll clear. And I'm going to stop sharing unless there's anything you want to have a question about. So we're out of time, so unless you have a question, I'm going to end the meeting for everybody. Any questions?
I got a private question to ask you.
Okay, what's that?
When I emailed the records office Wednesday, they never emailed me back.
And
So
what?
is there like another email I can send?
Okay, what was that about? I can't remember.
The Alpha Insurance.
Oh. They never emailed you back.
No.
When did you email them? Wednesday?
No, I had emailed them Thursday.
Thursday. Wow. They're usually pretty good about that. This time, go directly to Miss Chisholm, lchisholm@lawsonstate.edu, and also do B. Hyde, that's Hyde, Brenda Hyde, B. Hyde at lawsonstate.edu. Okay, Miss Chisholm is L. Chisholm, CHISEM, so it's the letter L, CHISEM at lawsonstate.edu. And then the Miss Hyde is B as in Brenda, HYDE at lawsonstate.edu. One of them will get back to you. I'm almost guarantee. I'm shocked that no one got back to you before, but it may have landed on someone's desk who's new and they didn't know what to do with it. They will know what to do with it. So when you send it to the records office, whoever gets it first, they have to do, and then they may have to wait and ask somebody and forget about it or something. But Miss Hyde and Miss Chisholm, they'll know.
Yes, sir.
And they should get back to you. Even if they can't do it, they should let you know who can. It may be financial services. I can't see why, but yeah, I think,
Yes, sir.
yeah, sorry about that.
You good? Thank you.
All right. Any other questions? Okay, I'm going to end the meeting for all of us, and take care. See you Wednesday.